Hi, welcome back to discussion on formulation of quantum mechanics. So in this small lecture, we are going to discuss what is the condition, what is the validity condition on the wave function. So when a function can be treated as a wave function. Okay. Now, the first of all, we know that the wave function is the state of the system in quantum mechanics, and it is a solution of time dependence from the equation. And the time dependence from the equation is given as minus h bar square by 2 dou square psi by dou x square plus v into psi of xt equal to ih cross dou psi by dou t. So this equation is one of the fundamental equation in quantum mechanics, and the solution is the wave function. So what are the properties of this wave function? Okay, now before going to this time dependence from the equation, we can first discuss time independence from the equation. If the potential is independent on time, then this equation would reduce to a simple equation. It's called a time independence from the equation. Now in time independence from the equation, again it is a second order derivative in space, and there is no time derivative here because it is independent on time. So the right side simply become e psi of x. And what is psi of xt? This psi of xt, now it is psi of x e raised to minus e t by h cross, where e is the energy. And psi of x is usually called the energy agent state or stationary state. Okay. Now the first property of this wave function is this wave function for any wave function psi of x, the second derivative must exist. If the second derivative is not existed, then this equation will not be valid. So that means in order to exist the second derivative, the wave function, the first derivative of the wave function and the wave function must be continuous. Okay, so recall this continuity and as well as the definition for the first derivative. The first derivative of any function df by dx, you can write limit delta x tending to 0 f of x plus delta x minus f of x divided by delta x. So this derivative will exist if f of x is continuous. Otherwise this derivative will not exist, because if the function has a certain discontinuity at any point, then the numerator would become a non-zero value and denominator will become 0 and it will tends to infinity. So if the function is not continuous, if f of x is not continuous at any point, then df by dx derivative at that point will be infinite. It means it is not existing. Okay, we can consider a simple example. So consider a function f of x. So f of x is suppose it is a up to a point x0, and it is b after x0. So the f of x equal to a for x less than x0, and it is equal to b for x greater than x0. Now what would be the derivative of the function exactly at the point x0? Okay, so according to this above definition, df by dx equal to limit delta x tend to 0. So you have to take an x just before an x0. So f of x0 minus delta x by 2 minus, and you have to take a point just after x0. So it will be f of x0 plus delta x by 2. Okay, it should be just opposite. So first we have to take the point after x0, and second we have to take a point before x0 divided by delta x, and this value, so limit delta x tending to 0. So the value of function just after x0 would be b, and just before x0 is a, so b minus a by delta x. And when this delta x approaches to 0, when delta x reduces, this b minus a will become fixed, will be fixed value, numerator will be fixed value, and denominator continuously decreasing, and its limiting value will go approach infinity. So the derivative will not exist at the location x0, but it exists at all points before x0 and all points after x0. The derivative exists, but it is not existed at exactly at the point of discontinuity. So here x0 is a point of discontinuity, and that the amount of discontinuity is finite here, because it is varying from a to b. So it is a finite discontinuity, and but even though the discontinuity is finite, the derivative will become the infinite at that location. So if the derivative become infinite, obviously the second order derivative would also become infinite. And so if the function is taking this kind of form, discontinuity, then we could not able to define a derivative of function as well as the second order derivative of the function. So no derivative is possible. Okay, so if you go back to our the original discussion, so here this can be written as, instead of d square psi by dx square, it should be d square psi by dx. So because the x is only function of x, so there is no need to write the partial derivative. We can write the total derivative itself. Okay, now this psi. So from this discussion, we can say that this psi must be continuous, and as well as the first derivative of psi should also be continuous. Then only we can define the second derivative. Okay, because this function must exist. This equation must valid at all points of x. So therefore, the psi must be continuous, and its derivative must be continuous at all points. Otherwise, there will be issue with the second derivative. Second derivative will become infinity, and this equation will not be valid. So that is the validity condition of the wave function. Okay. So for valid psi of x, first of all, psi of x must be continuous, and not only the psi of x, the derivative of psi of x must also be continuous, because if the derivative has certain discontinuity, then obviously the second order derivative will become infinite. So again, the Schrodinger equation will become invalid in those situations. So the derivative of the wave function must also be continuous. Now, if there is any other condition for the wave function, yes, indeed, there is one more condition, because we know that there is some physical meaning for this wave function. So there is no direct meaning for the wave function. Instead, there is a meaning for the wave function for its mode square. So remember, this mode square of the wave function is called the probability density. Okay, so it is the if you integrate mode psi square between 2 points, some x1 and x2, so it gives a probability to find the particle between the location x1 and location x2. Okay, so if you have some wave function mod psi of x squared, so it is of this form, Then if you integrate this mod size square between the x1 and x2 area under this curve, that will give the probability to find the particle. So this wave function obviously representing the wave function corresponding to some quantum particle. So the probability to find the particle between x1 and x2 is given by integral x1 to x2 mod psi square. Okay, now what will happen? What will be the result if you are integrating from minus infinity to plus infinity? That means if you are integrating over the entire length, the total length. So if you integrate the probability density of the total length, then definitely you must able to find the particle. So that means the probability to find the particle would be 1. So if you integrate mod psi of x square dx, and this must be 1. Now this is the another condition for the validity of wave function. So the wave function, in order to make wave function valid, the mod psi square, the integral of its mod square over the entire space must be 1. Now it can be 1, or in some cases it can be as it will be, you can write it can be as some constant c also. It is not an issue, because if it is equal to some constant c, it is always possible to find a normalized wave function. Okay, so if we can discuss it once again. So if the mod psi of x square dx equal to some constant, so that means this wave function is not normalized. So we can define a new wave function psi prime of x such that psi prime of x is psi of x divided by root c, and the mod psi prime of x square dx will become 1. So if you get the mod psi square dx equal to some constant, then it is always possible to find a normalized wave function psi prime such that its integral over the whole space will become 1. So it is also okay to get mod psi square dx equal to some constant also. It is not important to get its value equal to 1. If it is equal to some constant, then it is also an acceptable wave function. Okay, so we have three conditions for the validity of wave function, or there are three properties for the wave function. The first one is the wave function must be continuous, and second one, the derivative of wave function must also be continuous, and the third one, the integral of mod square of the wave function over the all space must be a constant. It can be 1, or it can be any other value. It should be a non-zero constant. It cannot be 0. It should be a non-zero constant. So here, so that also we can write. So here C must be non-zero. So these are the three properties or three conditions to check the validity of the wave function. If somebody is given a wave function to you, you can check whether it is correct or not by checking these three conditions. Okay, so thanks for watching this video. So we'll have an example of the quantum mechanics starting from with the symbol system. It's called the free particle system in the next class. Thank you.